Hello friend, today we are going to discuss one simple topic, carbon dioxide transport. Along with that, we will also discuss Haldane effect and Bohr's effect. Right? To understand this topic, first of all, you look at this schematic diagram. This is very simplified diagram. That is, oxygenated blood is carried by this systemic artery from the level of alveoli to the level of tissues. On the other hand, the deoxygenated blood is carried by the systemic veins from the level of systemic tissue up to the level of alveoli. Now, to understand the carbon dioxide transport, we have to remember certain numbers. That is, the partial pressure of carbon dioxide in arterial blood is equal to 40 millimeter of mercury. With a pressure of 40 millimeter of mercury, the carbon dioxide content, remember content means this is the amount of carbon dioxide, that is 48 milliliter per 100 ml or deciliter of blood. So please don't confuse between these two numbers. The partial pressure is 40 and the content of carbon dioxide is 48 ml per 100 ml of arterial blood. When this arterial blood reaches at the level of systemic tissue, we know tissue deliver 4 ml of carbon dioxide in 1 deciliter of blood. As a result of this, the content of carbon dioxide in venous blood reaches up to 52 ml per deciliter. Simple addition of 48 plus 4. So this is 52 ml per deciliter. Due to this increase in carbon dioxide content, the partial pressure of carbon dioxide reaches to 46 millimeter of mercury. So again I am telling you, don't confuse with the content with the partial pressure of carbon dioxide. Right. Now our job is to understand that how this extra 4 ml of carbon dioxide is transported by this venous blood from the level of tissue up to the level of alveoli. This is our class today, right? Now, before going into the detail of the transport process, remember one thing. We are discussing here carbon dioxide, but parallelly, if you want to remember what happens to oxygen, we know the amount of oxygen delivered from the arterial blood to the tissue is 5 ml from 100 ml of blood. In normal physiological situation, what happens when this venous blood is reaching at the level of alveoli? The simple thing, at the level of alveoli, the deliver of carbon dioxide will be 4 ml, obviously, because it is coming from the systemic tissues, and the amount of oxygen taken up at the level of alveoli will be also 5 ml in 1 deciliter of blood. So now, if we take a ratio of carbon dioxide production at the level of tissue upon the oxygen consumption, this ratio is known as respiratory quotient. Okay, so this is known as the respiratory quotient. So this respiratory quotient will be carbon dioxide production is 4 ml and oxygen uptake or consumption is 5 ml. So 4 upon 5, the ratio will be 0.8. I already told that under physiological condition, same amount of carbon dioxide is delivered at the level of alveoli and the same amount of oxygen is taken up from the lung. So if I take a ratio here also, that carbon dioxide output upon oxygen uptake. This ratio is known as respiratory exchange ratio. So this is respiratory exchange ratio, right? So obviously the respiratory exchange ratio will also be 0.8 under physiological condition. So please remember, although we are describing the same thing, but if we use the tissue and this blood compartment, then we are using the word respiratory quotient. But whenever we are taking the carbon dioxide output and oxygen uptake between this alveoli and this blood compartment, we are using the word respiratory exchange ratio. Otherwise, the ratio according to the number, it's exactly the same. Okay, now we are moving on to the next part, that how the carbon dioxide is transported in venous blood, in which format, in which forms. Okay, so carbon dioxide transport occurs through plasma also, as well as RBC also transport carbon dioxide. In the plasma or in the RBC, the format or the forms by which the carbon dioxide is transported is number 1, dissolved form of carbon dioxide, number 2, carbamino compound. So I'm writing like this: curve amino compound formation, and third, carbon dioxide will form bicarbonate. So I'm writing bicarbonate formation, right? Similarly, inside the RBC, all these three forms will be seen. That is the dissolved carbamino compound, and third, bicarbonate formation. Okay. Now, if you want to remember the percentage of carbon dioxide transported by different forms, first of all, remember dissolved form of carbon dioxide in plasma as well as in RBC is 5%. 5% means total 10% of carbon dioxide is transported via dissolved form. So what is the amount of carbon dioxide transported from the tissue to the level of lung? We have already discussed that the total amount of carbon dioxide transport by venous blood is 4 ml per 100 ml blood. So within this 4 ml, only 10% is transported via dissolved form. Dissolved means that is a carbon dioxide mixed up with the water portion of the plasma or water portion of the RBC. Then second, carbamino compound. Look at the percentage, important here. The percentage of carbamino compound inside the plasma is only 1%, but the percentage inside the RBC is 21%. So the thing is, why the carbamino compound is more inside RBC? Now remember, carb-amino compound formation means carbon dioxide is attached with the amine radical of either plasma protein or hemoglobin. So if the carbon dioxide is attached with the amine group of plasma protein, this is known as carbamino compound of plasma. And if the carbon dioxide is attached with amine group of hemoglobin, that is the carbamino compound of RBC. Now, which percentage or which amount will be more? So I am asking you, what is the concentration of this protein in plasma? Okay, amount. We know कि plasma protein is approximately 8 gram percentage. But if I ask you, what is the percentage of hemoglobin inside the RBC? That is the hemoglobin concentration, mean corpuscular hemoglobin concentration, or MCHC. That is approximately 33%. So which percentage is more? Obviously, the percentage of hemoglobin is more than percentage of plasma protein, because of which the available amine group is more inside the RBC, and that's why the percentage is huge as comparison to plasma. Fine. Now coming to the bicarbonate formation or bicarbonate forms. Inside the plasma, the bicarbonate forms is only 5%. Okay, and how the bicarbonate will form, we'll discuss this a little later, but I hope you all know this bicarbonate formation is due to reaction of carbon dioxide with water, which will form the carbonic acid, which later on divides into bicarbonate forms. Now inside the plasma, the reaction is very slow. On the other hand, if you look at the percentage of bicarbonate inside the RBC, this is 63%. That means the major fraction of carbon dioxide is transported by bicarbonate forms, and this bicarbonate formation mainly occurs inside the RBC. Question is why? I told you already, the reaction of bicarbonate formation in the plasma is a very slow reaction, but inside the RBC, the reaction is catalyzed by an enzyme, that is carbonic anhydrase, and due to presence of this carbonic anhydrase, the reaction becomes approximately 5,000 times faster at the level of RBC, due to which the maximum amount of carbon dioxide transport occurs via this forms. Am I clear? So now if you look at the various percentage here, okay, at the level of plasma, dissolved form, carbamino compound, and bicarbonate form. So total approximately 11% of carbon dioxide is transported by plasma, and on the other hand, the total amount of carbon dioxide transported by RBC is 89%. So major fraction by the RBC only, right? And RBC. Okay. So now you look at this schematic diagram, very simplified diagram. Okay. So this is the systemic tissues. Okay. And as you are seeing here, this is the capillary. So you are seeing the lumen of the capillary, and inside this capillary, this is a big RBC, right? First of all, the tissue will produce carbon dioxide, and the amount is 4 ml, that will be delivered in 1 deciliter of blood. So carbon dioxide, being a gaseous molecule, will easily penetrate the capillary endothelium, and it will enter inside the plasma. That this carbon dioxide inside the plasma will be transported via 3 formats. First of all, dissolved carbon dioxide, right? Second, carbamino compound formation, which is carbon dioxide along with plasma protein, and also small amount of bicarbonate formation will occur. But this is not the major form of carbon dioxide transport. So what happens? This carbon dioxide will further enter inside the RBC. Okay. Again, inside the RBC, small amount of carbon dioxide will form the dissolve, small amount in the form of carbamino compound. But the main carbon dioxide that will be transported inside the RBC is bicarbonate forms. how it will occur? The carbon dioxide will react with water. As a result of this, carbonic acid will form, and this is catalyzed by the enzyme carbonic anhydrase. Okay. Now this carbonic acid will divide into H plus ion and bicarbonate ions. Okay. This H plus ion will be stabilized by or will be accepted by the hemoglobin. Okay, I'm coming to this point a little later. Okay, but because of the acceptance of this H plus ion by hemoglobin, what happens? More and more bicarbonate formation will occur inside the RBC. Means this reaction, although it's a reversible reaction, the reaction will move from left side to right side. As a result, the amount of bicarbonate become huge inside the RBC. Now, what is the fate of this bicarbonate? This bicarbonate will be exchanged with the plasma chloride ions. So you are seeing here that chloride ion is entering from the plasma in exchange with bicarbonate ion from the RBC. As a result, what happens? The chloride content of RBC in venous blood a little more, and the plasma chloride content is less. This exchange process is done by a transporter protein. This transporter protein is known as anion exchanger protein. So this is a chloride bicarbonate antiporter, which is also known as the anion exchanger or band 3 proteins of RBC. Okay, right? Now, due to this exchange process, what happens? The chloride content of the RBC increases. Due to increase in the chloride content, the osmolality of RBC also increases. Now, whenever the osmolality of the RBC is high, we all know what is going to happen. That is, entry of water from plasma to RBC. This is nothing but osmosis of water from low solute concentration of plasma to the high solute concentration of RBC. Due to entry of this water, what happens to the size of RBC? Simple, the size of RBC increases. Okay, due to which theoretically the packed cell volume of venous blood is 3% higher than the arterial blood. So please remember, although it's a theoretical concept, but for physiology and for MCQ purpose, this is an important one. Okay, so due to entry of this chloride inside the RBC, the osmolality is higher, because of which it is taking up water from the plasma, due to which the size as well as the packed cell volume increases. So this whole process of chloride exchange is known as chloride shift phenomena, or this is also known as Hamburger's effect, or this is also known as Linnaeus phenomena. This is also known as Linnaeus phenomenon, right? Now we are coming to what is the fate of this H plus ion. What is the fate of this H plus ion? Now please remember, at the level of tissue, the blood which is reaching here is obviously the oxygenated blood. Oxygenated blood means the hemoglobin is attached with the oxygen. So I'm writing like this. This is oxygenated hemoglobin. I told you already that this H plus ion will react with the oxygenated hemoglobin. As a result, what happens? So H plus ion reacting with the oxygenated hemoglobin. This will leads to formation of deoxygenated hemoglobin and release of oxygen from hemoglobin. So please remember this, that H plus ion is accepted by hemoglobin. That means it is acting as an acid-base buffer. But what is the end result? End result is that there is release of oxygen from hemoglobin. Now this oxygen, being a gaseous molecule, will easily penetrate the RBC membrane first, and then it will penetrate the capillary endothelium and will be delivered at the level of tissue. So this is oxygen release at the level of tissue. So what we are finding here, look at carefully. If the carbon dioxide content of the blood increases, oxygen release occurs at the level of tissue. Or I can say that carbon dioxide is ultimately producing this H plus ion. Due to high amount of H plus ion, oxygen release occurs at the level of tissue. This is known as Bohr's effect. Okay, so release of oxygen from hemoglobin in presence of carbon dioxide or H plus ion. Bohr effect is described with the help of oxygen hemoglobin dissociation curve. It's a separate topic, you have to read it later on. But look at oxygen hemoglobin dissociation curve. X-axis is the partial pressure of oxygen and y-axis is the oxygen content. We all know that the oxygen hemoglobin dissociation curve shape is like that of a sigmoid shape. Okay. In presence of huge amount of carbon dioxide or huge amount of H plus ion, we all know there will be right shifting of this curve. So I'm writing here right shift of this curve. Okay, so this right shift of curve, if it is occurring due to high carbon dioxide or high H plus ion, this is also known as Bohr's effect. Okay, so I hope this is clear. So Bohr effect, if you look in books, it will be written like this, that the effect of carbon dioxide or H plus ion on hemoglobin's affinity for oxygen is known as Bohr effect. In some other books, it is written that there is decrease in oxygen affinity of hemoglobin with a decrease in pH. That means if the H plus ion is high, the pH will decrease. This will lead to decreased affinity of oxygen. And sometimes it is also described like this, that rightward shift of the oxygen equilibrium curve or oxygen hemoglobin dissociation curve resulting from increased carbon dioxide or increased H plus ion is known as Bohr's effect, right? Now we have to understand that what happens to this venous blood when it is reaching at the level of lungs, right? We know at the level of alveoli, the oxygen tension is very high. Now when this oxygen is entering inside the capillary, it will directly reach inside the RBC. So oxygen diffusion inside the RBC. Now please recall, the blood which is reaching at the level of alveoli, this is a deoxygenated blood. That means the hemoglobin is in deoxygenated form. So I'm writing here, this is the deoxygenated hemoglobin. So in presence of oxygen, this deoxygenated hemoglobin will react. This will give rise to oxyhemoglobin formation again. Very simple. At the level of lung, oxygenation of hemoglobin is occurring. Now please remember, the oxyhemoglobin is a strong acidic molecule as comparison to deoxygenated hemoglobin. Okay. So strong acid means it's a proton donator. Okay, means this oxyhemoglobin will not be able to hold the H plus ion or proton further. So it will release the H plus ion. So this is H plus ion release. Now this H plus ion will combine or react with bicarbonate ion. So the H plus ion is reacting with bicarbonate ion, which will leads to formation of carbonic acid again in presence of carbonic anhydrase. So question is, what is the source of this bicarbonate? Because we have seen in venous blood, bicarbonate was diffusing out of the RBC, and this diffusion was due to presence of a chloride bicarbonate antiporter. Remember, at the level of alveoli, this chloride bicarbonate antiporter reverses. That means it takes up the bicarbonate ion again from plasma and it sends the chloride ion back to the plasma again, due to which we can easily understand that the chloride content of the arterial blood a little higher than venous blood. Now, due to movement of the chloride out of the RBC, the osmolality of RBC, obviously it will reduce. Now, this carbonic acid will divide into obvious carbon dioxide and water molecule. Because the osmolality of the RBC is already low, the water has to move out of the RBC, so water is going out, due to which the size or the PCV is lesser than that of the venous blood. So we can see here that all the reaction already occurred at the level of venous blood is reversing here at the level of arterial blood or at the level of alveoli. Now, what is the fate of this carbon dioxide? Very simple. Carbon dioxide, being a gaseous molecule, will easily penetrate the RBC membrane, and from there it will be released at the level of alveoli. So release of carbon dioxide at the level of alveoli. So I can say like this, that in presence of oxygen, hemoglobin molecule is releasing its carbon dioxide. Okay, this release of carbon dioxide in presence of oxygen is known as Haldane's effects. This is known as Haldane's effect. Fine. So I hope this is clear. Bohr effect is occurring at which level? Look here. So this is occurring at the level of tissue, and Haldane's effect is occurring at the level of lungs. Please remember. Now the Haldane's effect is described with the help of carbon dioxide dissociation curve. Please remember, we have discussed the Bohr effect with the help of oxygen hemoglobin dissociation curve, but the Haldane effect is described with carbon dioxide dissociation curve. X-axis of this curve indicate the partial pressure of carbon dioxide, and y-axis of the curve indicate carbon dioxide content. And look at the shape of this curve. This is almost linear. This is not the sigmoid shape like that of the oxygen hemoglobin dissociation curve. So how this curve is described? But before that, look at how the Haldane's effect is described in bookish language. Okay, so as you can see here, it is clearly written that when oxygen binds with hemoglobin, carbon dioxide is released to increase carbon dioxide transport. Language of Guyton's and Hall's physiology. Okay, similarly, some other books are saying that binding of oxygen with hemoglobin molecule in the pulmonary capillaries tends to displace carbon dioxide from hemoglobin. So now we are going to discuss the Haldane effects with the help of carbon dioxide dissociation curve. Look at this curve carefully. The x-axis of the curve indicate partial pressure of carbon dioxide and y-axis is the content of carbon dioxide, right? This 46 partial pressure is a feature of venous blood, and obviously 40 is the carbon dioxide partial pressure of arterial blood. Now if I draw a perpendicular on this dissociation curve, and if we draw another perpendicular on y-axis, what we are finding out that with a partial pressure of 46, the content of carbon dioxide in venous blood is 52 ml, right? So if we draw another perpendicular from this arterial blood carbon dioxide partial pressure, we are finding out that the content of arterial blood carbon dioxide is 50. So the difference between venous blood and arterial blood carbon dioxide is only 2 ml. But this is not the actual scenario. Remember, when oxygenation occurs, what happens? The dissociation curves shifts in a downward direction. This is the new dissociation curve position. When this shifting will occur, when there will be oxygenation of hemoglobin at the level of lung. So means when the partial pressure of oxygen is 40, the curve is in an upward position. But when the oxygenation of hemoglobin is occurring, the curve is shifting in a downward direction. Now if we draw a perpendicular on this new curve, okay, what we are finding out, see here. So this is the perpendicular touching the y-axis at 48 value. That means when the partial pressure of carbon dioxide is 40, the content of carbon dioxide is 48 ml, and this is happening due to the downward shifting of this curve. That means now we can appreciate from here that the difference of carbon dioxide content between arterial blood and venous blood is 4 ml, and this difference is due to downward shifting of this curve. Otherwise, if the curve is not shifting, we have already discussed the difference between arterial and venous blood carbon dioxide is only 2 ml. That means the shifting is doubling the carbon dioxide difference between artery and venous blood. And the shifting of the curve is nothing but the Haldane's effect. That's why in Guyton's and Hall textbook of physiology, it is clearly written that Haldane's effect doubles the carbon dioxide transport in venous blood. And how much is the total amount? That is the 4 ml in 100 ml blood. If there is no Haldane effects, so the curve will not shift in a downward direction, and the carbon dioxide transport will be 50% of the original value. This is all about the carbon dioxide transport. Okay,